Finally it works. Hello, what I was doing there was testing a light controller I made for RC vehicles and robots. I'm controlling some LEDs, but the same method could be used to control more complicated things as well. The main point of this project is to get the signal from the receiver to the microcontroller. The microcontroller in this case is PSOC 4 chip. This board also includes 3.3 volt regulator and 3 sets of MOSFETs and resistor for external LEDs. I designed this PCB to do one thing, and that is to control 3 sets of LEDs. If I have RC car that drives, I can add this circuit with LEDs and have controllable headlights. By following this video, you should be able to read the signal from the receiver with the PSOC chip and use that information in your projects as you will. Quick word about this video sponsor who also supplied these PCBs. PCBWay.com is an affordable PCB manufacturer who also offers 3D printing and CNC milling services. You can get a handful of good quality 2-layer PCBs for just $5 plus shipping. That's the starting price for basic PCBs, but they can do much more advanced PCBs as well if that's what your project needs. PCBWay is a great PCB manufacturer for all your prototyping and low volume production needs. Go check out their current pricing and capabilities at PCBWay.com. I really like PSOC 4 line of microcontrollers from Cypress. This cheapest PSOC 4 chip don't have many of those advertised advantages of most other PSOC chips, but it is still 32-bit microcontroller that can be configured using the same PSOC Creator IDE, which I like. In case you are not familiar with RC devices, the RC receiver outputs a PWM signal with pulse width between 1 millisecond and 2 milliseconds depending on the position of the switch or potentiometer on the transmitter. This signal is good for an electronic speed controller or servo motor because they have a decoder inside them translating incoming pulses length into a certain speed or position. But this signal isn't any good for driving LEDs, not without some kind of decoder in between. Thankfully, this signal is simple, so we can read the pulse length and use that as a variable in our microcontroller's code. In this case, I'm going to set up the input signal to control the timer in a way that will trigger an interrupt at the falling edge of the pulse, and the pulse length is available immediately after the interrupt. Hardware will handle restarting and reloading the timer. In the code, we just read the pulse length value and use it as we want. So let's get started with the software. In PSOC Creator, let's create a new project, select correct device and an empty schematic as a starting point. Even this, one of the simplest PSOC chips, can be configured using this schematic editor by dragging components from the list to the schematic sheet. For this project, I need a timer in a capture mode. Timer can be found under Digital and Function. This timer will be used to measure pulse length. Run mode of the timer should be one shot because it only runs during the pulse. Rising edge on the input should reload counter with 0 and start the timer. Falling edge should capture the current value of the timer and stop it. I need to expose reload, start, stop and capture pins to the schematic. Stop and capture inputs should be changed from default rising edge to falling edge to match our requirements. I will also change the interrupt settings to trigger interrupt on the compare/capture count. This component needs a clock as an input. It can be found under System. The frequency of this clock isn't all that important, but it affects the captured counter values later on. I decided to use 1 MHz, so 1 tick is an easy to understand 1 microsecond, and thus servo signal will be represented by counter values from 1000 to 2000. The timer is now set up correctly and I need to add input and few outputs. The input can be digital input pin under ports and pins with its default configuration. The same input signal will control all the functions of this timer component, so I will connect reload, start, stop and capture inputs together and all those to the input pin. Last thing I need to connect to this component is interrupt, found under System. Changing the name is recommended for clarity, nothing else needs to be changed. At this point, the the timer component will measure the length of the pulses on the input pin, and the length value is available after the interrupt triggers. What else is needed depends on what you want to do with the circuit. In my circuit, output will be for 3 sets of LEDs. I will add 3 output pins, but I will disable hardware connections in configuration because they will be only controlled in the software side. Now I have input and couple of outputs, and I can select which pins of the IC those are in the Design Wide Resources. In this Pinout tab, it's clear that debugging interface is using 2 valuable pins. I can use those pins as I/O pins by disabling the debugging interface in the System tab of this Design Wide Resources window. I'll change the debug select from SWD to GPIO. When I go back to Pins tab, those pins are free to be used for other things. I will start assigning the pins starting from the most specialized function. The input signal is used as an input for the timer component, and when selecting which pin it should be connected to, there's only one option, which I will obviously select. The outputs are just GPIO pins, and there are no restrictions on which I/O pins I could use. I'll select the 3 free pins on the right side of the chip. After making changes in the schematic editor or Design Wide Resources, it's a good idea to go to Build menu on the top and click Generate Applications. This will check your design and update the APIs so the component and function names get recognized in the code editor. This will include and generate the sources reflecting your design choices. These hardware configurations I've just made are doing the heavy lifting. In the code I need to write interrupt service routine to get the measured pulse length. Inside the ISR, I will read the captured timer count and set the state variable based on the value. To prevent interrupt from triggering repeatedly, the interrupt needs to be cleared inside the ISR. In the main function, timer needs to be initialized and just written ISR needs to be assigned to the interrupt. Then I can control the LEDs in the endless loop based on the variable set inside the ISR. The main thing I want to share with you is measuring the pulse length using BSOC's timer component. I hope this was helpful if you had problems with this application. Thank you for watching. Thanks. Bye.